industry where 100 meter per minute speed. Where I go to, if any breaks, we go to the paper machine, the pop reel, we take the paper and then see. If you want to know the temperature or moisture, we just touch and feel the heat. From there, we are into the big data. With AI, maybe AI also kind of outdated now. So we are coming into the Gen AI and then super artificial intelligence. Many things are already there with us. Now I quickly go with. Okay, can I use this? I quickly go through it. What is big data? From there, and then what the type of a data collection we can do for the data collection or the sheet breaks or for the matter of fact any optimization. And then what is the methodology we use? What are the steps we follow it? And then what are the benefits? Maybe benefits can be easily feel. And then there are I go through all this with a case studies, few case studies. I don't know. I have time for this. So the big data, there are four V's. One is volume. The name itself says the big data. The tons of data available already with the paper machines. So are we using it? Before that, so the variety of data, we know there are QCS, DCS, drives, multiple varieties of data are also available in the paper machine. And then velocity, which means the sampling rate. What are the sampling? Maybe we can use the QCS sensor produce almost 1,000 hertz data, which is 1 millisecond data already we have. And then we have a drives data, lab data, we have a text data, we have pictures, videos from the paper break or conditional monitoring system. So are we using it? Here, if you see this, the big data, the another V, maybe veracity, which means the bad data. Any bad data will mislead us, mislead the analysis. So we have to make sure the data are good. So we have to remove all the outlays and other things, and then all other the fifth V is value. So how do we use the big data to minimize the sheet break? What normally I do, this most of the paper makers what we do in paper machine. The first step we collect the data, right, and then different type of data are available, and then we go for a measuring phase. When you measure, we have to come up with some numbers, and then we have a goals, the benchmark which TAP standard or some other people coming with the benchmarks. We compare both current performance and then what is the current status of that machine. Once we are done, then we go for some recommendation and then improvement phase, and then we come up with the advanced phase. Maybe I can explain the last slide. What is advanced? How do we use the big data to go with artificial intelligence? So the data, we know we have a lot of data available. When I ask, are we using it? So we know how many percentage of data we use for the decision making in any industries, process industries. Shockingly, it's less than 4% of data we are using for the decision making. So, for example, here we have a lot of data available, QCS, DCS, drives. Maybe, for example, the real report. Real report is a very good tool for paper makers. But are we using those numbers to make some decisions? And then we have a lot of high frequency equipment data, lab data, and then the pulp. The pulp data, for example, this pulp data is kind of an island. So we don't, in the paper machine side, the data are not that available. So quickly, what methodology we follow? So before in this data collection phase, for example, the QCS and DCS. The QCS and DCS, we collect 5 seconds data. The sampling units are 5 seconds, and then we need a long duration. That is what in the real report it says MDL and MDS, right? So the MDL means the long term, which is coming from the back. MDS means short term, which is coming from the machine, which is like a rotating rolls or wires and files like that, or vibration or vacuum issues. That is in the MDS. Yeah. For example, here, what I do before we go to the analysis, I understand from the pulp mill what type of a pulp we are making it. In the pulp mill, we have a hash factor or kappa number, whatever you call it as. We have a lot of data are also available in the pulp mill. We track them, how it is coming to the digester, what is the current condition of that digester, and then we move to bleaching or washing and bleaching, and then we have a storage in the paper machine, and then I quickly go to the refiners. Refiners, as he explained, lot of other factors also in the refiners, which also will give us lot of problem in the paper machine for the brakes. So we understand all this. We have to come up with some. So when I do the manually, I quickly go through all this and then come up with pulp strength. What is the pulp strength of the machine? And then what is the paper strength? See, when you go for the pulp strength, and then you just mix in the blending with a different furnish, and then go for chemical addition, and then paper strength. And then we understand the pulp strength, and then we categorize the brakes. From there, and we have to little bit understand what is your wire life, felt life, something like that. And then if we have a web brake monitoring, we can use that videos or pictures to understand more. Once everything is done, for example, we do process index. Maybe quickly go through one index. For example, this. Maybe if you want to know, I can quickly go through this. So, for example, this is one example. See here, the ash. We collected 100 bricks. Just example, 100 bricks in 1 month. And then quickly go through all the informations. The product variability, like ash, we have some variations. And then this happens in 14 times in 1 month. Just an example. This is the case, real case study. I'm trying to explain 100 bricks. Out of 100, 14 bricks are from the ash. This hash variations. Maybe there are process variability. We don't know what process variability, and then we have to go with that and then understand the process variability, how it affects the product variability. Once we understand, then we have to solve this problem. Say kind of things, maybe headbox variation, chemical variations, or your vacuum variations. So this is a classical example. We have a chemical here. We have a chemical, it was running fine, and then the chemical variations 41 times we observed there are a lot of variabilities in the chemical, different kind of a chemical. And then we see the breaks within 5 minutes or 10 minutes. Just example, here in this case 6 minutes, right? So if we see this type of a problem, we know what is happening at the back. We can understand with a lot of data. We have a lot of data at the back. With that, we analyze and then improve this case. So by doing all this, by understanding all this, one more point, the the golden run. For example, we know, everyone knows now, with the data, we can come up with the golden run. We have a set of data which you produce a best kind of a without break, good runnability. And then with that data, we can have a kind of benchmark, and then you compare with the real data, the current data, and then we understand this, and then we go with a sensitive index. This is how I do it in the manually, and then I go with a problem-based solution. The solutions may be with control data utilization or control problems, or your freeness, as he explained, freeness problem, unstable stock delivery. The stock, from the stock to the head box, there are multiple equipments are there. So how they are delivering to the machine, we have to understand that dynamics, and then we have wet end variability with the chemicals, all this, and then how the paper machine is responding in manual and automatic mode. When we understand all this, and then I come up with a improvement program. So once you improvement program, first thing is I go through this real report, and then I quickly explain this one. This is what I'm trying to explain to the paper the paper makers. For example, the condition weight. We have a goal. What is your variability? Let's say 3. 1.5 is the condition weight goal. 3 is your current condition. And then we know there are huge variations. And then the next step is, okay, we have variation, where it is coming from. Maybe we have a 3 category, MDS, MDL, CD. Once we understand where is MDL, for example, some issues are there, which is coming from the stock. And then we dig down again, we have to deep dive into the problems. We have a steps 1, 2, 3. And then we go into MDL, which portion of the machine or stock preparation is causing that problem. The same way MDS is the machine issues, rotating. So we collect high frequency data. That data collection portion is different. So we collect the high frequency data, we understand the MDS. From there, if it is CD, you know that CD is your cross direction. For example, this is the indication. This is the kind of a overview indications. So we have to understand all this and then improve. That's the improvement program. Once I understand this, and then we have to go for the refiner optimization and then stock stabilization. Again, I want to quickly go through this. For example, we have a n number of, for example, one control loop, which means it has pipeline, it has a pumps, it has a tanks, it has the transmitters, how the transmitters are set, where the transmitters are installed, where are the valves, pumps, and then what the equipment is doing. All this information is in one control loop. We analyze all your 100 or 300 loops in your stock preparation. Once we understand all this, for example, I come up with 3 areas or 4 areas. One is the signal, how the transmitters are behaving. If the transmitter gives us bad indications, like we drive the car, if we see the bump or speed breaker, we slow down and then go. If we don't see, if we put some black glass, we don't see that, and then we are jumping or hitting there. Same way, the controls will do that. If you have a right setup in the data, and then, for example, this is your example. You have some straight lines. No flows are doing that. But we have some dead bands or filtering at the, damping at the kind of your transmitters. That will give that type of a data. Here, there are 2 reasons. When I remove, you can see the real data. So you can, the improvement, the visibility is improved. First thing is, the paper maker see the data, right data. Second thing is, the control does the good job. That's a bad data, gives you the valve variation. When the valve variation, you are inducing the energy or inducing the variation to the machine, which will definitely cause the problems. Same way, for example, this loop tuning. We have this is very small, 2% level variation. This is very big, not small. 2% is very big. That gives you a lot of issues, right? When we do a right tuning number, so these adjustments are, if you understand the process, then adjusting the tuning number is very small, very simple. There are only 2 numbers. When you do, you can see the improvement in a straight line, right? If you have all your process, all your control loops, if it is like this, imagine the stability of the machine. So same way, that is a classical case, my favorite. See, one of the machine, maybe time is working, I don't know how to finish. Maybe that is a classical case. When you see, there was a machine, that machine runs at 0.22 sigma on 100 GSM. It's a really classical machine. If the 2 sigma has gone to 0.4, so customer called me. And then I know last 10 years I was working there. So there is no tuning possibility because I put the number, I calculated, I put that number. There is no possibility. But if you see here, they introduced one chemical. So that chemical created this is a stock flow before tuning, after tuning. The chemical created some spiky measurements. When you have a spike measurements, it's not a real. It's a spiky induced by the chemical. That time your valve will operate, right? When your valve is operating, you have inducing the variation to the machine. The same way when I and then requested a customer to change the location, so we have a straight line in the stock flow. So once you are done with all your loop performance, once we are done with all your loop performance, then we come to the product variability. So this, for example, here, this is the one of, I'll explain only this slide. So behind this slide, 1 month of my time, customer's investment is there. This is not only the variation reduction. If you see, I can produce this data for longer period, maybe 2 days, 3 days. Which means variability reduced. Second is no disturbance at the back. There is no disturbance, no breaks, right? There, here, when you do like this, then we can go for the optimized set points for each and every parameter. For example, whatever he is doing, the refiner freeness control, the freeness variation has been reduced. But what is it a right optimized set point? Is it a specifically is it optimized or not? How do we know that? So from here we can take it up. Maybe I quickly complete this. So the transition, yes. When we do, there are two areas. One is stability, second is agility. The stability, the two sigmas are low for all your process. Agility means when you step change, when you change the grade, or if you have any upset, how long you take it brought back to the original stage. For example, here, for example, that one. So one loop, just example, one loop. I changed the set point. It was taking 240 seconds or 250 seconds to complete to reach that. And then once you are doing the tuning, it reduces the time. Same way, when you change the set point of or grade change, the stock is coming faster. But at the back end, your consistency, flow, or your color, or your filler, everything should come in the right place. That is what that grade change is all about. But that is what we have to complete that production, the implementation. I'm done. I'm done. Okay. Finally, this is very important. Actually, sorry. This is actually important. See what I did. Everything as I've done manually. I collect the big data. I collect different datas and then do manual analysis. Go for a solution. Now I come up with a. We have see. We have a. I partnered with the AI specialist, and then now we come up with automatic way. Please, last 1 minute. Let me complete only this. Okay, so we come up with a automatic analysis. There are two things. One is automatic analysis, give you the reasons 1, 2, 3, top 3 reasons or 5 reasons. Next is how to predict. Prediction is really possible. We installed or implemented in 2 customers. One is pulp sheet machine, another is paper machine, high speed machine, very high speed machine. Even for me, it is shocking. The accuracy is 80 to 85%, which is that is what that AI capabilities are. Maybe we are still working on. See, the paper machine is fighting with me to give that result, but still we are working on that. Let's see how to improve that. This is sales slide, so let me stop it, and then finally I have done this manual analysis in number of places across the globe. We have done everywhere, many machines, name it, writing, printing, or tissue paper or board paper, whatever it is. Okay. Oh, sorry, I forgot to introduce. Good afternoon to all. My name is Kannan. I'm working with OptiPA. I just freelancer. I'm working for paper machine optimization solution. Thank you.
So thank you, Kannan, for a wonderful presentation. Very good.